Hello, in this last lesson, first we want to discuss an application of the derivative to the study of equations with real solutions. More precisely, we are talking about Rolle's method to find the number of real solutions of an equation. We start with Rolle's theorem. Now, Rolle's theorem says the following. Let's take a function defined on the closed interval AB, taking values in the set of real numbers, which is continuous and is differentiable on at least the open interval AB. So at the points AB is not necessary to be differentiable, but it must be continuous. If f of A equals f of B, that means at the ends of the interval, the function takes the same value, then the theorem says there exists an element C between A and B such that the derivative of f at the point C must be 0. Attention, the number C is not necessarily unique. So the theorem says only that it does exist. Maybe there are more than one. Okay. Now the idea is very simple. I shall not make the proof, but just to have an intuition. If at the points A, B, the function takes the same value, then the graph of the function must start from here and stops here. Loosely speaking, we are in the situation when let's say for instance, the graph is increasing, and then to come back at the point at the same value as in the beginning, it must decreasing and then increase again. So obviously these are the points where the derivative will be 0 because they are extrema, and according to Fermat theorem, the derivative must be 0 here. So on this picture there are 2 points, C1 and C2, where the derivative of f must be 0. This is not the proof, but it's the intuition behind the proof. Okay, now let's see applications. The usual and the most important application is to find the number of the solutions of an equation. Suppose, for example, we have an equation f of x equals 0, with x, the unknown x in some interval, and we would like to know the number of the real solutions. How many real solutions the equation has? This is the question we want to answer. Okay, so the idea is to apply the previous theorem. Let's make the following observation first of all. Suppose, for example, that x1 and x2 are solutions of our equation. So that means f of x1 equals f of x2 equals 0. That means they are equal. So on the interval x1, x2, if the conditions of the previous theorem are fulfilled, then there must be a point C between x1 and x2, where is the derivative must be 0. Again, I repeat, if the conditions of the theorem are fulfilled on the interval x1, x2. So we can state this property as follows. Between two solutions of the equation f of x equals 0, there must be at least one solution of the equation f prime of x equals 0. So, of course, we suppose that x1, x2 is inside an interval on which the function is defined. We are talking about intervals just. So if x1 is here and x2 is here, if f vanish at both x1 and x2, then there must be at least a point C between them where the derivative vanishes. So between two roots of f, there must be at least one root of the derivative. There could be also two. For example, we may have this picture. Okay. Now, if we see the reverse of this statement, one can observe that between two consecutive roots of the derivative, there could be at most one root of the function f. So this is what we need. So if so between two consecutive solutions of the equation f prime of x equals 0, there is at most one solution of the equation f of x equals 0. So the idea of the algorithm is to solve the equation f prime of x equals 0, and these solutions will separate the solutions of the equation f of x equals 0. So we can somehow count the number of the real solutions of our equation. Okay, the algorithm following from the method is the following. Consider the equation f of x consider the equation, so which is not necessarily written f of x. We have an equation. The first step is to write the equation as f of x equals 0, then find the domain of f, then compute the derivative of f. Of course, we shall suppose that, as usual, that f has a derivative, so we are working with differentiable functions. Then solve the equation f prime of x equals 0, which has several solutions, call them C1, C2, C3, for example. And then we put all together in a table, which is as follows. It has two rows, x and f of x. On the first row, we put the domain of the definition. Let's suppose it is the set of real numbers, for example, but not necessarily. And also the critical points, namely the solutions of the equation f prime of x equals 0. And now we compute the sign of f at these values, including the limits of f at minus infinity and infinity. Suppose, for example, that we need only the sign, not exactly the value. So suppose, for example, the limit at minus infinity is 2, then we have here plus. The value at C1, let's say it's 5, then we have here plus. The value at C2 is minus 1, for example, we would be here minus. Let's suppose here we have again minus, and then we have the limit at infinite. Suppose it is infinite, so it's plus. Okay, so we have here 5 signs, and now the question is, how many roots of f do we have on the interval, on each interval, on the interval minus infinity C1? So here what we observe is that f doesn't change the sign, So here there are no solutions. Here F changed the sign. So there is at least one solution, but according to Rolle theorem, there is at most one. Here we have exactly one solution. Here there are no solutions, and here we have again one solution. For example, in this hypothetical table, the equation f of x equals 0 has two solutions, x1 between the numbers c1 and c2, and x2 between c3 and infinity. Okay, anyway, we know how many solutions, real solutions, has the equation f of x equals 0, and moreover, we separate them. I mean, we know an interval for each solution. Okay, let's illustrate now this method on an example. Let's start with a very simple example. Let's consider, for example, x at 3 minus 3x plus m equals 0. So we have the equation written, let's take it without a parameter, which I'll discuss later on. Let's put here plus 1. So this solution, how many real solutions has this solution? It has this equation. So we consider, we must make a choice for f. We consider f of x be this one. The domain of definition is the set of entire set of real numbers. Then we need to compute the derivative, which is 3x squared minus 3. Then we need to compute the solutions of the equation f prime of x equals 0, which are plus and minus 1. I shall denote them by x1 and x2, not like in this algorithm here with c1, c2. Okay. And now we can put all together and have the table. The domain is the set of real numbers. Here the critical points were minus 1 and 1. And now let's see the sign of f on both, on each element here. The limit at minus infinity of f of s is minus infinity, obviously, so this is minus. The limit at infinity, it's plus infinity, here it's plus. The value of f at minus 1, f of minus 1 equals minus 1 plus 3 plus 1, that is 3. So it's positive. And the value of f at 1 will be minus 1, it's negative. So according to this table, now we know that the equation, our equation here, has 3 real solutions. Let's denote them by x1. Of course, they have nothing to do with this. x1 is between minus infinity and minus 1. x2 is between minus 1 and 1. And x3 is between 1 and infinity. The most important is that we found that our equation has 3 real solutions. That's important. Okay. Let's consider another example. Let's consider the following equation. For example, x minus 2 equals square root of s squared plus 1.